Quantum mechanics gives us equations. Those equations work. They predict atomic spectra, the behavior of semiconductors, the decay rates of unstable nuclei. They've been tested to extraordinary precision across decades of experiments. But there's a moment in every quantum calculation where the mathematics stops and something else begins. A transition that isn't described by any equation in the theory. Physicists have been arguing about this for nearly a century, not because the equations fail, but because they succeed too well. It happens when you move from what the formalism tells you exists to what you actually see when you look. The equations themselves describe something called the wave function, often written as ESI. This mathematical object evolves according to the Schrödinger equation, which is deterministic. If you know the wave function at one moment, you can calculate it at any future moment with complete certainty. The evolution is smooth, continuous, reversible. Nothing jumps, nothing chooses. But measurements don't behave this way. When you measure a quantum system, when you check the position of an electron or the spin of an atom, you get one result. Not a spread of possibilities, not a smooth distribution. One number, one outcome. And if you prepare identical systems and measure them again, you get different results, distributed according to a specific probability rule. This rule wasn't derived from the Schrödinger equation. It was added to the theory as a separate postulate by Max Born in 1926. The Born rule tells you how to extract probabilities from the wave function. You take the amplitude for each possible outcome, square its absolute value, and that gives you the chance of seeing that outcome. It's remarkably successful. It matches every experiment we've done. But it doesn't follow from the rest of quantum mechanics. It stands outside the formalism, introduced specifically to connect theory to observation. The problem isn't that the Born rule fails. The problem is that quantum mechanics requires two incompatible descriptions of how systems evolve. When you're not measuring, the wave function evolves according to Schrödinger's equation, deterministic, continuous, reversible. When you perform a measurement, the wave function collapses, stochastic, discontinuous, irreversible. These are fundamentally different processes, and the theory gives no account of when one applies versus the other, or what physically distinguishes a measurement from any other interaction. This tension will reappear in every proposed resolution, but it will not take the same form each time. This is what physicists call the measurement problem. It's not a problem about experimental technique. It's not about whether we have precise enough instruments. It's a conceptual gap in the structure of the theory itself. Quantum mechanics tells you how to calculate what will happen in almost every circumstance, but it doesn't tell you what a measurement is, or why measurements behave differently from everything else the theory describes. The standard response historically has been to accept this division as fundamental. The Copenhagen interpretation, though it's more accurate to call it a family of views rather than a single doctrine, essentially treats measurement as a primitive concept that can't be reduced further. You have quantum systems, which obey Schrödinger's equation, and you have classical measuring devices, which record definite outcomes. The measurement process bridges these two domains, but the theory doesn't describe the bridge itself. Niels Bohr emphasized that we need classical concepts to even formulate what we're measuring. We can't describe a measurement outcome without referring to macroscopic classical properties, pointer positions, screen flashes, detector clicks. In this view, the quantum classical divide isn't a flaw in the theory. It's a necessary feature of how we acquire knowledge about the world. But this raises immediate questions. What counts as a measuring device? Where exactly does the quantum domain end and the classical domain begin? Is it at the level of atoms, molecules, the apparatus, the observer's retina? The boundary seems arbitrary. If measuring devices are made of atoms, and atoms are quantum systems, then why should the measurement process escape quantum description? One attempt to address this involves decoherence. When a quantum system interacts with a large environment, air molecules, thermal radiation, stray electromagnetic fields, the different branches of its superposition become entangled with different environmental states. This environmental entanglement destroys the coherence between branches, making interference effects effectively impossible to observe. The system starts to behave classically, not because the wave function has collapsed, but because the quantum correlations have spread out into the environment beyond practical recovery. Decoherence explains why macroscopic objects don't exhibit quantum interference. It shows why superposition becomes invisible at large scales, but it doesn't explain why you see one particular outcome when you perform a measurement. The wave function still contains all possible results, just entangled with the environment. Decoherence tells you why the superposition is hidden, not why one branch becomes real. Some physicists argue this is enough. If interference effects are destroyed and different outcomes are effectively isolated, then for all practical purposes, the wave function has collapsed. But this pragmatic approach doesn't resolve the conceptual issue. The theory still describes a superposition, even if we can't observe it, and measurements still produce single, definite results that the formalism doesn't predict. Another approach denies that collapse happens at all. Hugh Everett proposed this in 1957. In his framework, the Schrödinger equation is the only law. It applies universally, without exception. When a measurement occurs, the wave function doesn't collapse. Instead, it evolves into a superposition that includes both the quantum system and the measuring device, and eventually the observer. From this perspective, all measurement outcomes occur. The universe branches into multiple non-interacting components, each representing a different result. You, as an observer, also split. Each branch contains a version of you who sees one particular outcome. From your subjective viewpoint, measurements appear random because you experience only one branch, but the theory describes all branches as equally real. This removes the need for collapse. There's only one dynamical rule, the Schrödinger equation, and it never breaks down. But it introduces other difficulties. If all outcomes occur, what does probability mean? Why should you expect to see certain results more often than others when every result happens in some branch? Everett and later proponents have offered derivations of the Born rule within this framework, but these remain controversial. The ontological status of the branches is also unclear. Are they physically real worlds or just mathematical components of a global wave function? Whether this reframes the problem or merely relocates it remains disputed. A different class of approaches modifies quantum mechanics itself. Objective collapse theories add non-linear stochastic terms to the Schrödinger equation that cause spontaneous collapse at random intervals. These collapses are rare for individual particles, but become frequent for macroscopic systems, which explains why we don't see quantum interference in everyday objects. The Ghirardi-Rimini-Weber model, proposed in the 1980s, is one such theory. It postulates that each particle undergoes spontaneous localization at a rate of about once every 100 million years. For a single particle, this is negligible, but a macroscopic object contains trillions of particles, so the cumulative effect causes rapid collapse. Roger Penrose has suggested a related idea tied to gravity. He argues that superpositions involving different space-time geometries are unstable and collapse due to gravitational effects. When the gravitational self-energy difference between superposed states exceeds a certain threshold, roughly 1 Planck mass, collapse occurs. These theories make collapse a physical process independent of observation. They predict deviations from standard quantum mechanics that can, in principle, be tested. Recent experiments have begun to constrain their parameters, ruling out some versions while leaving others viable, but they remain speculative, and it's unclear whether modifying quantum mechanics is necessary or merely one possible solution. What all these approaches share is an attempt to resolve the tension between the two dynamics, the smooth evolution of the wave function and the abrupt transition during measurements. But none has achieved consensus. The measurement problem persists, not because physicists lack ideas, but because each resolution requires accepting something conceptually difficult. You can accept a fundamental divide between quantum and classical domains, but then you face the boundary problem. You can deny collapse and embrace universal wave function evolution, but then you must interpret what the branches mean. You can modify the theory to include objective collapse, but then you introduce new dynamics without clear physical motivation. The problem isn't about finding the right interpretation. It's about recognizing that the theory, as it stands, has an unresolved structure. Quantum mechanics works extraordinarily well for making predictions, but it doesn't explain its own connection to experience. It tells you how to calculate probabilities, but not what happens when a measurement occurs, or why measurements should be treated differently from other physical interactions. This isn't a failure of the theory within its domain. It's a limit of what the formalism can explain. The equations describe the evolution of quantum states with remarkable accuracy, but they stop before describing the transition from quantum possibilities to classical actualities. That gap has remained open for nearly a century. The measurement problem is often presented as a puzzle to be solved, a mystery awaiting the right insight. But it may be more accurate to see it as a structural feature of quantum mechanics, a place where the theory requires an external notion of measurement that it cannot define within its own framework. Whether this will eventually be resolved by a deeper theory, or whether it reflects something fundamental about the limits of physical explanation, remains an open question. What's clear is that the problem isn't going away through incremental refinement. Every interpretation, every modification, every attempt at resolution brings its own conceptual costs. And the core tension between deterministic evolution and stochastic outcomes, between smooth dynamics and abrupt transitions, continues to define the conceptual landscape of quantum mechanics. The theory works, but explaining why it works and what it means for reality to behave this way remains beyond the reach of the equations themselves. The mathematics describes a system evolving smoothly through time. The equations are deterministic. They predict, with perfect precision, how a quantum state will change from one moment to the next. There are no gaps in the formalism, no undefined terms, no moments where the theory stops working, and yet, when you perform a measurement, something different happens. The smooth evolution stops, the system snaps into a definite state. The equations that governed everything up to that point no longer apply. This isn't a failure of experimental technique. It's not about imperfect instruments or human error. It's a structural feature of the theory itself. Quantum mechanics provides two distinct rules for how systems change. One rule governs what happens when you're not looking. The other governs what happens when you are. And there's no principle within the theory that tells you when to switch between them. What makes this unusual is that both rules are indispensable, yet they cannot be unified within the same dynamical framework. This is the measurement problem. It's not a paradox in the usual sense. The math doesn't contradict itself. The predictions match experiments to extraordinary precision, but the theory requires you to treat measurement as fundamentally different from every other physical process. Without explaining what measurement is or when it occurs, you have to impose that distinction from outside the formalism. The difficulty is not predictive failure, but explanatory incompleteness. Start with what the theory does successfully. A quantum system is described by a wave function, a mathematical object that encodes all possible measurement outcomes and their relative probabilities. When the system is left alone, the wave function evolves according to the Schrödinger equation. This evolution is unitary, meaning it preserves information and allows interference between different possibilities. If you know the wave function at one time, you can calculate it at any future time with complete certainty. This works perfectly for isolated systems. An electron in a magnetic field, a photon propagating through space, an atom transitioning between energy levels, all of these follow the Schrödinger equation without exception. The theory makes precise predictions about interference patterns, energy spectra, and transition probabilities. It accounts for the stability of matter, the behavior of semiconductors, and the structure of molecules. At this level, quantum mechanics is extraordinarily successful. But then you measure the system. You detect the electron's position, or the photon's polarization, or the atom's energy state, and you always get a single, definite result. Not a superposition of possibilities, not an average. One outcome, the wave function, which was evolving smoothly according to the Schrödinger equation, abruptly changes. It collapses onto the measured state. The other possibilities, which were still present in the mathematics just before measurement, disappear. This transition is instantaneous, non-unitary, and stochastic. It doesn't follow the Schrödinger equation. It follows a different rule, the Born rule, which assigns probabilities to measurement outcomes based on the wave function's amplitude. So the theory has two dynamics, one for undisturbed evolution, one for measurement, and nothing in the formalism tells you what constitutes a measurement or when the transition occurs. The formalism simply assumes that such a transition takes place without specifying its physical origin. This isn't a problem you can solve by improving the math. The Schrödinger equation is fully specified. The Born rule is fully specified. The issue is that they are incompatible as descriptions of a single continuous physical process. Either the wave function evolves unitarily or it collapses. It can't do both. The theory switches rules without providing a mechanism for the switch itself. The obvious response is to define measurement more precisely. Maybe collapse occurs when the system interacts with a macroscopic apparatus. But the apparatus is made of atoms. Those atoms obey quantum mechanics. So the combined system, quantum object plus apparatus, should also evolve according to the Schrödinger equation. The wave function of the combined system should enter a superposition where different measurement outcomes correspond to different apparatus states. No collapse should occur. This is the core tension. If you treat measurement devices as quantum systems, they don't collapse wave functions. They become entangled with them. The superposition spreads outward, encompassing the apparatus, then the laboratory, then the observer. Nothing in the equations singles out a moment where this stops and a definite outcome appears. Some approaches try to locate a boundary. The Copenhagen interpretation, in its various forms, accepts measurement as a primitive concept. It divides the world into quantum systems and classical measuring devices. The quantum system evolves unitarily until it interacts with a classical apparatus, at which point collapse occurs. But this division is arbitrary. There's no physical principle that tells you where to place it. Is the boundary at the detector, the recording device, the scientist's eye, the neurons in their brain? Niels Bohr argued that classical concepts are necessary for describing measurements because they're needed to communicate results. Werner Heisenberg suggested collapse reflects the transition from potential to actual. John von Neumann pushed the boundary all the way to consciousness, arguing that only a conscious observer could collapse the wave function. But none of these proposals emerge from the mathematics. They're interpretive additions imposed to make the theory connect with experience. They function as conceptual bridges rather than derivations from the formalism. Another approach denies that collapse happens at all. Hugh Everett's many worlds interpretation treats the Schrödinger equation as universally valid. The wave function never collapses. When a measurement occurs, the universe branches. All possible outcomes are realized in different branches, each corresponding to a different version of the observer. From any single observer's perspective, they see one definite result, but globally, all results occur. This eliminates the need for a separate collapse rule, but it introduces new difficulties. If all outcomes occur, what does probability mean? Why do we experience the Born rule frequencies? Everett argued that probabilities reflect the weights of different branches, but deriving the Born rule from pure unitary evolution remains contentious, and the ontology raises questions. Are the branches equally real? Do they physically exist, or are they just terms in a mathematical expansion? Here, the measurement problem is not removed, but reframed in terms of ontology and probability. A third approach modifies the theory itself. Objective collapse models add stochastic terms to the Schrödinger equation that cause spontaneous collapse at random intervals. For microscopic systems, these terms are negligible. But for macroscopic systems with many particles, the cumulative effect causes rapid collapse, producing definite measurement outcomes without requiring an external notion of measurement. These models make testable predictions. They suggest slight deviations from standard quantum mechanics that could be observed in sufficiently precise experiments. Recent tests have begun to constrain their parameters, ruling out some versions while leaving others viable. But they remain speculative. It's unclear whether modifying quantum mechanics is necessary or whether the problem can be resolved within the existing framework. What's common across all these approaches is that they require accepting something conceptually difficult. The Copenhagen interpretation requires an unexplained boundary between quantum and classical domains. Many worlds requires accepting that all measurement outcomes occur in parallel branches of reality. Objective collapse requires introducing new dynamics without clear physical motivation. There's no resolution that preserves both the mathematical structure of quantum mechanics and our intuitive understanding of measurement as revealing pre-existing properties. This isn't just a philosophical inconvenience, it's a structural limitation. The theory works extraordinarily well for making predictions, but it doesn't explain its own connection to experience. It tells you how to calculate probabilities. It doesn't tell you what happens when a measurement occurs, or why measurements should be treated differently from other interactions. That explanatory gap is built into the framework, not imposed from outside it. The problem isn't that physicists lack ideas. Dozens of interpretations have been proposed. The issue is that each interpretation involves trade-offs that many find unacceptable. You can keep the mathematics unchanged and accept observer-dependent reality. You can modify the equations and introduce new collapse mechanisms. You can eliminate collapse entirely and accept a vastly multiplied ontology, but you can't have it all. Unmodified quantum mechanics, objective measurement outcomes, and a single definite reality. Some argue this reflects a deeper truth about the limits of physical theory. Maybe quantum mechanics isn't incomplete. Maybe it's complete within its domain, and that domain simply doesn't include an account of measurement. The theory describes how systems evolve, not how they produce experiences. That's not a flaw, it's a boundary. Others maintain that the problem will eventually be resolved by a more fundamental theory, quantum gravity, or a deeper understanding of space-time, or a framework that unifies quantum mechanics with general relativity. The measurement problem, in this view, is a symptom of our incomplete understanding, not a permanent feature of reality. But for now, the tension remains. Quantum mechanics requires you to treat measurement as special without defining what makes it special. The equations work, the predictions match experiments, but explaining why they work and what they mean for the nature of reality remains beyond the theory's explanatory reach. The problem persists not because physicists haven't thought hard enough, but because the structure of the theory itself contains this unresolved element. And recognizing that limitation, acknowledging where the formalism stops and interpretation begins, may be the most honest position available. The theory of quantum mechanics predicts the probabilities of measurement outcomes with extraordinary precision. For systems like electrons in atoms or photons in optical cavities, the mathematical framework generates numbers that match experimental results to 15 decimal places. The equations work, the predictions hold, but the theory itself contains no mechanism for explaining how a system that exists in multiple states simultaneously produces a single, definite result when measured. This isn't a gap in experimental technique or a limitation of current technology. It's a structural feature of the formalism itself. The Schrödinger equation describes how quantum states evolve over time. It's a deterministic equation. Given an initial state, the equation tells you exactly what state the system will be in at any later time. The evolution is smooth, continuous, and reversible. Nothing in this evolution singles out particular states as special. A particle doesn't have a definite position. It has a wave function that assigns amplitudes to all possible positions. An electron doesn't spin in a particular direction. Its state is a superposition of spin-up and spin-down components. The mathematics treats these superpositions as the fundamental reality of the system. But when you perform a measurement, something different happens. The superposition disappears. The system produces a single outcome. An electron registers as spin-up or spin-down, not both. A photon is detected at one location, not at multiple locations simultaneously. The wave function, which previously described a spread of possibilities, now corresponds to a single, definite state. This transition from superposition to single outcome is called wave function collapse. And it's not described by the Schrödinger equation. This creates a conceptual problem. If quantum mechanics is supposed to be a complete description of physical systems, then measurement itself should be describable within the theory. A measuring device is made of atoms. Those atoms obey quantum mechanics. The interaction between a quantum system and a measuring device should therefore be governed by the same deterministic evolution that governs everything else. But if you apply the Schrödinger equation to the combined system of particle plus measuring device, you don't get collapse. You get a larger superposition. The device becomes entangled with the particle, entering a superposition of having detected spin up and having detected spin down. Nothing in the mathematics forces a single outcome. This is the measurement problem. The theory requires two incompatible rules. One rule governs how systems evolve when left alone. Another rule governs what happens during measurement. There's no clear criterion for when to apply which rule. The boundary between quantum and classical behaviour isn't specified by the theory itself. It's imposed by the physicist analysing the system. Some might argue this isn't a genuine problem. Quantum mechanics is an empirical theory. Its purpose is to predict measurement outcomes, not to explain the metaphysics of measurement. As long as the predictions work, the formalism is doing its job. This is roughly the position associated with the Copenhagen interpretation, though that label covers a range of views. In this pragmatic approach, measurement is treated as a primitive concept. It's not reducible to deeper quantum processes. The theory tells you how to calculate probabilities given that a measurement occurs. It doesn't explain what constitutes a measurement or why measurements have different dynamical rules than other interactions. This works for practical purposes. Physicists can use quantum mechanics to design experiments, build quantum computers, and develop new technologies without resolving the measurement problem. But it leaves conceptual questions unanswered. If measurements are fundamentally different from other physical processes, what makes them different? Is there a physical property that distinguishes measuring devices from quantum systems? Or is the distinction observer-dependent, reflecting how we choose to describe the situation rather than an objective feature of reality? The theory functions operationally while remaining conceptually unfinished. One possibility is that the problem arises from applying quantum mechanics beyond its domain of validity. Quantum mechanics might accurately describe microscopic systems while breaking down for macroscopic objects like measuring devices. The collapse of the wave function might represent the transition from quantum to classical physics, even if the theory itself doesn't explain why this transition occurs. This would suggest that quantum mechanics is incomplete, not in the sense of being wrong, but in the sense of requiring supplementation by a theory of measurement that goes beyond the Schrödinger equation. In this view, the problem reflects a mismatch of scale rather than a flaw in the microscopic laws. Another approach denies that collapse happens at all. In the many worlds interpretation, proposed by Hugh Everett in the 1950s, the wave function of the universe evolves deterministically according to the Schrödinger equation at all times. When a measurement occurs, the universe doesn't collapse into a single outcome. Instead, it branches into multiple, non-interacting versions, each corresponding to a different measurement result. From the perspective of an observer within one branch, it appears that a single outcome occurred. But globally, all outcomes exist in separate branches of the universal wave function. This interpretation eliminates the need for a separate collapse postulate. The appearance of definite outcomes is explained by decoherence, a process in which interactions with the environment effectively separate the branches, so that interference between them becomes unobservably small. But it raises new questions. If all outcomes occur, what determines the probability of finding yourself in a particular branch? The Born rule, which assigns probabilities to measurement outcomes, is a postulate in standard quantum mechanics. In many worlds, it's unclear why observers should experience outcomes with frequencies matching the Born rule if all outcomes actually happen. Attempts have been made to derive the Born rule from the structure of the many worlds framework itself, typically using decision-theoretic arguments about rational betting behaviour. These derivations remain controversial. Some physicists find them convincing, others argue they introduce hidden assumptions that effectively smuggle in the Born rule rather than deriving it. The status of probability in a deterministic, branching multiverse is one of the unresolved aspects of this interpretation. Here the difficulty shifts from dynamics to meaning. A different class of proposals modifies the Schrödinger equation itself. Objective collapse theories add stochastic terms that cause the wave function to spontaneously collapse at random intervals. For individual particles, these collapses are rare enough that quantum superpositions persist long enough to produce interference effects. But for macroscopic objects containing vast numbers of particles, the cumulative effect of many individual collapses causes rapid reduction to a single state. This provides a dynamical mechanism for wave function collapse without invoking observation or measurement as special categories. These theories make testable predictions. They suggest small deviations from standard quantum mechanics that could be detected in sufficiently sensitive experiments. Recent tests using optically levitated nanoparticles have begun to constrain the parameters of some collapse models, ruling out certain versions while leaving others viable. But introducing new dynamics raises questions about why these collapse terms exist and what physical mechanism underlies them. Without a deeper theory motivating the collapse process, these models remain phenomenological descriptions rather than fundamental explanations. They trade conceptual economy for explanatory completeness. The common thread across these approaches is that each requires accepting something conceptually difficult. The Copenhagen interpretation requires an unexplained boundary between quantum and classical domains. Many worlds requires accepting that all measurement outcomes occur in parallel branches. Objective collapse requires introducing new dynamics without clear physical motivation. There's no interpretation that preserves both the mathematical structure of quantum mechanics and our intuitive understanding of measurement as revealing pre-existing properties. Every resolution moves the difficulty rather than eliminating it. This isn't simply a matter of philosophical preference. The measurement problem has practical implications for developing quantum technologies. Quantum computing relies on maintaining superpositions of many qubits while preventing premature collapse through decoherence. Understanding the precise boundary between quantum and classical behavior matters for engineering systems that exploit quantum effects. Similarly, proposed tests of quantum mechanics at increasingly large scales depend on knowing what predictions the theory actually makes when applied to macroscopic objects. The problem also connects to attempts at unifying quantum mechanics with general relativity. Both theories work extraordinarily well within their domains, but they're built on incompatible foundations. General relativity treats space-time as a smooth, classical background. Quantum mechanics requires treating everything as quantum, including potentially space-time itself. The measurement problem highlights a tension that any unified theory would need to resolve. How does a fundamentally quantum universe give rise to the appearance of classical definiteness? Any successful unification would have to explain not only dynamics, but definiteness itself. Some argue this reflects a deeper limitation. Perhaps quantum mechanics isn't incomplete. Perhaps it's complete within its domain, and that domain simply doesn't include an account of measurement. The theory describes how systems evolve. It doesn't describe how they produce experiences or observations. That's not a flaw, it's a boundary. This position suggests the measurement problem might not have a solution within physics. because it's asking physics to explain something outside its explanatory scope. Others maintain the problem will eventually be resolved by a more fundamental theory, quantum gravity, a deeper understanding of space-time, or a framework that unifies quantum mechanics with general relativity. The measurement problem, in this view, is a symptom of incomplete understanding rather than a permanent feature of reality. But for now, the tension remains. Quantum mechanics requires treating measurement as special without defining what makes it special. The equations work. The predictions match experiments. But explaining why they work and what they mean for the nature of reality remains beyond the theory's reach. The problem persists not because physicists haven't thought carefully enough, but because the structure of the theory itself contains this unresolved element. Recognizing that limitation, acknowledging where the formalism stops and interpretation begins, may be the most intellectually honest position currently available. The measurement problem doesn't indicate that quantum mechanics is wrong. It indicates that the theory, despite its empirical success, doesn't explain its own connection to observation. And that gap between mathematical formalism and experiential reality defines the boundary of what quantum theory can currently tell us about the world. It is a boundary of explanation, not of usefulness. The equations that describe quantum systems work. They work so well and with such precision that they've been tested across energy scales spanning dozens of orders of magnitude. They predict interference patterns, atomic spectra, particle decay rates, and quantum correlations with extraordinary accuracy. Yet the theory contains a structural discontinuity that has never been resolved. The mathematics describes how quantum states evolve continuously through time according to the Schrödinger equation, a smooth, deterministic process that preserves all information about the system. But when physicists extract predictions from this formalism, they invoke a second process, measurement. And measurement behaves nothing like Schrödinger evolution. It's discontinuous, probabilistic, and irreversible. The theory requires both processes but provides no criterion for when one applies versus the other. This is called the measurement problem. It's not a question about what happens during experiments. It's a question about why quantum mechanics needs two fundamentally incompatible rules for how physical systems change. One describes continuous evolution, the other describes discrete, random outcomes. Both are necessary for making predictions. Neither explains when the transition between them occurs. Consider what the Schrödinger equation actually does. Given the state of a quantum system at one moment, it determines the state at any future moment. The evolution is linear. If you start with a superposition, a combination of multiple possible states, the equation preserves that structure. A system in a superposition of two states at time zero remains in a superposition at all later times. This linearity is fundamental to quantum interference, entanglement, and essentially every distinctly quantum phenomenon. But measurements don't preserve superpositions. They yield single definite outcomes. When you measure the spin of an electron that's in a superposition of spin up and spin down, you get one result, either up or down. Not both, not a superposition. The wave function, as described in standard textbooks, collapses to match the observed outcome. The formalism includes a rule for calculating probabilities, the Born rule. Square the amplitude of each component in the superposition, and you get the probability of observing that outcome. This rule works. It's been verified in countless experiments across every domain where quantum mechanics applies. But it's not derived from the Schrödinger equation. It's an additional postulate, and it introduces randomness into a theory whose fundamental evolution is deterministic. The tension isn't subtle. If everything in the universe follows quantum mechanics, including measuring devices, laboratory equipment, and physicists, then the entire process of performing a measurement should be describable by the Schrödinger equation. The device, the system being measured, and their environment should evolve unitarily, maintaining superposition throughout. There should be no collapse, no single outcome, no moment when probability becomes actuality. Yet we observe single outcomes. The formalism predicts them, using the Born rule, but it doesn't explain them. It doesn't specify what constitutes a measurement, when collapse occurs, or what physical mechanism underlies the transition from superposition to definite result. John von Neumann analysed this structure carefully in the 1930s. He showed that you could place the boundary between quantum and classical systems at any point in the measurement chain without affecting predictions. The electron could collapse when it interacts with the detector, or the detector remains in superposition until the signal reaches recording equipment, or the equipment remains quantum until a human observer looks at the readout. Von Neumann's mathematics allowed all these placements. The theory itself provided no criterion for choosing among them. This flexibility might seem like a strength. The theory works regardless of where you draw the line. But it reveals something troubling. If the location of the cut is arbitrary, then the theory isn't describing a feature of physical reality. It's describing a limitation in the formalism itself. Quantum decoherence, developed extensively since the 1970s, addresses part of the issue. When a quantum system interacts with a large environment, the different components of its superposition become entangled with different environmental states. This entanglement destroys the coherence between superposition branches, making interference effects practically impossible to observe. A system that's decohered by its environment behaves, for all observable purposes, as if it's in a definite state rather than a superposition. Decoherence explains why macroscopic objects appear classical. It explains why we don't see interference patterns in everyday life. It solves what might be called the appearance of collapse problem. Why the world looks definite even if the underlying quantum state remains in superposition. But decoherence doesn't solve the measurement problem. It doesn't explain why, when we perform an actual measurement, we observe one specific outcome rather than all of them. The wave function after decoherence is still a superposition. It's just a superposition whose branches no longer interfere with each other. The question of why we experience one branch rather than remaining aware of all branches remains unanswered. Some interpretations accept this limitation and place the boundary openly. The Copenhagen interpretation, in its various formulations, treats measurement as a primitive concept. It divides the world into quantum systems and classical measuring devices. The transition between them is where collapse happens. This approach doesn't pretend to explain collapse. It accepts it as the point where the formalism connects to experience. The cost is conceptual. If measuring devices are made of atoms, and atoms follow quantum mechanics, then treating measurement apparatuses as fundamentally classical creates an unexplained division within physics. It works, but it leaves a seam visible in the theoretical structure. Other approaches try to eliminate collapse entirely. The many worlds interpretation proposed by Hugh Everett asserts that the Schrödinger equation is complete and universal. Nothing ever collapses. When a measurement occurs, all outcomes happen. The universe branches, and each branch contains an observer who experienced one specific result. From inside any branch, measurements appear to produce single outcomes with probabilistic frequencies. But globally, no collapse occurs. This interpretation eliminates the discontinuity at the cost of ontological extravagance. It requires accepting that reality consists of vast numbers of parallel branches, almost all of which are inaccessible to any observer within a given branch. It also faces challenges explaining why the Born rule probabilities should match the observed frequencies of outcomes if all outcomes occur with equal ontological status. Objective collapse theories take a different path. They modify the Schrödinger equation itself, adding nonlinear terms that cause spontaneous collapse of superpositions. In the GRW model, developed by Gherardi, Rimini, and Weber, collapse happens randomly for individual particles at a very low rate. For single atoms, collapse is so rare it's undetectable. But for macroscopic objects containing trillions of particles, the collective collapse rate becomes high enough that superpositions decay almost immediately. These theories make testable predictions. They suggest that superpositions of sufficiently large objects should collapse faster than standard quantum mechanics predicts. Recent experiments testing quantum superpositions of increasingly massive particles have begun constraining the parameter space, where such theories could remain viable. The window is narrowing, but hasn't closed. Roger Penrose proposed a related mechanism linking collapse to gravity. His argument is that superpositions create superpositions of space-time curvature, and that gravity resists such configurations. When the gravitational self-energy difference between branches reaches a threshold, the superposition becomes unstable and collapses. This would provide a physical basis for the collapse process, grounded in quantum gravity effects that standard quantum mechanics ignores. The proposal shifts the problem from interpretation to dynamics, but at a significant theoretical cost. The hypothesis is speculative. We lack a complete theory of quantum gravity, so any mechanism invoking it operates beyond established physics. But it illustrates a broader point. Explaining measurement might require going beyond quantum mechanics, as currently formulated. In this sense, the proposal functions more as a signal than a solution. What none of these approaches can do is preserve both the completeness of unitary evolution and the definiteness of individual measurement outcomes without accepting some conceptually difficult consequence. Copenhagen accepts a fundamental quantum classical divide. Many worlds accepts vast ontological proliferation. Objective collapse theories introduce new dynamics without clear physical motivation from existing theory. Each option resolves the tension by relocating it. The measurement problem persists because quantum mechanics, despite its empirical success, doesn't explain why its mathematical structure connects to observed outcomes the way it does. The Born rule works, but it's not derived from more fundamental principles within the theory. Collapse happens or appears to happen, but the formalism doesn't specify when or how. The link between calculation and observation is assumed, not explained. This isn't a sign that quantum mechanics is wrong. It's a sign that the theory has boundaries. It describes how systems evolve and predicts measurement outcomes with remarkable accuracy. But it doesn't explain the relationship between these two aspects of its structure. That relationship remains external to the formalism. The gap is structural, not empirical. Some argue this reflects a limitation not of physics, but of what physics can explain. Perhaps the theory describes physical systems and their evolution, but not the process by which those systems produce experiences or observations. That wouldn't make quantum mechanics incomplete within its proper domain. It would just mean that domain doesn't include an account of how abstract states become concrete outcomes. On this view, the discomfort arises from misplaced expectations rather than theoretical failure. Others maintain that a deeper theory will eventually resolve the tension. Quantum gravity, a more fundamental understanding of space-time, or some framework that unifies quantum mechanics with general relativity. The measurement problem in this view is a symptom pointing toward physics we haven't yet discovered. Whether this hope reflects precedent or optimism remains unclear. For now, the gap remains. Quantum mechanics requires treating measurement differently from ordinary evolution without explaining what makes measurement special. The equations work. The predictions match experiments across every tested regime. But the theory doesn't explain its own connection to the definite world we observe. What remains unresolved is not prediction, but meaning. That explanatory gap isn't hidden in some obscure corner of the formalism. It's built into the structure at the most fundamental level, in the difference between how quantum states evolve and how measurements produce results. Recognizing this limitation means accepting that one of our most successful physical theories contains an unresolved element at its core, not a mystery to be solved through deeper insight into existing concepts, but a genuine boundary where the mathematical framework stops providing answers. The difficulty appears not at the margins of the theory, but at its point of contact with the world. The measurement problem isn't a puzzle with a solution waiting to be found. It's a place where quantum mechanics, as currently formulated, simply doesn't extend. The theory describes quantum systems with extraordinary precision. It predicts measurement outcomes with perfect accuracy, but it doesn't describe measurement itself. That operation remains external, imposed from outside the quantum formalism. Whether future physics will absorb measurement into a unified framework, or whether measurement represents an irreducible aspect of how theories connect to observation, remains an open question. What's certain is that quantum mechanics, despite being our most fundamental description of physical reality, leaves this connection unexplained. The success of the predictions does not eliminate the explanatory silence. The theory accounts for how a single electron interferes with itself when passing through a barrier. It predicts the energy levels of hydrogen atoms. It explains tunneling, entanglement, and the statistical behavior of identical particles. These aren't approximations, they're exact solutions to the Schrödinger equation, verified across millions of experiments. Few theoretical frameworks have earned comparable empirical confidence, but when you close the mathematical loop and ask what happens when you actually perform a measurement, when you check whether the electron went left or right, when you verify which energy level the atom occupies, the formalism becomes silent. Not imprecise, silent. The equation that governs everything before measurement simply stops applying. A different rule takes over, and quantum mechanics offers no physical account of when or why this transition occurs. The shift is assumed, not derived. This isn't about improving experimental techniques. It's not about building more sensitive detectors or isolating systems better from environmental noise. The problem exists at the level of mathematical structure. The theory requires two incompatible descriptions of time evolution, and it provides no criterion for choosing between them. One description preserves information and generates interference. The other destroys information and produces definite outcomes. Both are necessary for connecting theory to observation. Neither explains when to apply the other. The incompatibility is formal, not practical. You could place the boundary anywhere. Von Neumann proved this formally in 1932. The electron could collapse when it hits the detector. The detector could remain quantum until the signal reaches recording equipment. The equipment could stay in superposition until a physicist reads the data. The mathematics permits all these choices. The predictions don't change. But this flexibility reveals something troubling. If the location of collapse is arbitrary, then collapse isn't describing a physical process. It's describing a limit of the formalism. The freedom is mathematical, not ontological. Decoherence explains why we don't see macroscopic superpositions. Environmental interactions spread quantum correlations outward, making interference effects vanish for practical purposes. A dust grain in superposition decoheres in microseconds, a bacterium in nanoseconds. This solves the appearance problem, why the world looks classical even if the underlying state remains quantum. But appearance isn't the issue. The issue is why any particular outcome occurs. Decoherence shows how branches become separate. It doesn't explain why you find yourself in one branch rather than experiencing all of them. It accounts for suppression, not selection. Some frameworks eliminate collapse by keeping everything quantum. Everett's many worlds interpretation extends unitary evolution indefinitely. All measurement outcomes occur in separate branches. Observers split along with the systems they measure. From inside any branch, measurements appear random and definite, but globally, no randomness exists. This preserves the mathematical structure completely. It also requires accepting that reality constantly multiplies into non-interacting versions of itself, and that probability in a deterministic theory needs reinterpretation. The price is paid not in equations but in ontology. Other approaches modify the Schrödinger equation. Objective collapse models add stochastic terms that cause spontaneous reduction of superpositions. For single particles, collapse is negligible. For macroscopic objects, it happens fast enough to suppress quantum behavior. These theories make testable predictions. Collapses generate heat, create slight deviations from standard interference patterns. Experiments are beginning to constrain the parameter space. Some versions are ruled out, others remain viable. But introducing new dynamics raises the question of what physical mechanism drives collapse, and why that mechanism takes the particular mathematical form it does. The modification explains outcomes by assumption rather than necessity. Penrose suggested linking collapse to gravitational self-energy differences between superposed states. When the difference exceeds roughly 1 Planck mass worth of energy, he argues, space-time can't sustain the superposition and reduction occurs. This would root collapse in quantum gravity effects. But we don't have a theory of quantum gravity, so any proposal invoking it operates beyond established physics. It points toward where an explanation might come from without providing the explanation itself. The idea functions as a placeholder for deeper structure. What's common across all these approaches is that none preserves every desirable feature. Copenhagen-style interpretations accept a quantum classical boundary without locating it. Many worlds preserves unitary evolution, but requires vast ontological commitment. Objective collapse theories introduce new physics without clear motivation. Each trades one conceptual difficulty for another. There's no interpretation that keeps the mathematics intact, explains definite outcomes, and avoids conceptual costs. Resolution always arrives with conditions attached. This isn't because physicists haven't thought carefully enough. It's because the structure of quantum mechanics itself contains this tension. The theory works. It predicts with extraordinary precision. But it doesn't explain the connection between its mathematical objects and the definite outcomes those objects are used to predict. That connection remains external to the formalism, supplied by the Born rule. imposed through measurement, operationally necessary but theoretically unexplained. The bridge is functional, not structural. The Born rule assigns probabilities based on wave function amplitudes. Square the amplitude, get the probability. It works perfectly, but it's a postulate, not a derivation. Attempts to derive it from more fundamental principles within quantum mechanics remain contentious. Some arguments appeal to decision theory, constructing rational betting strategies that reproduce Born rule probabilities. Others use symmetry principles or typicality measures. None has achieved consensus. The rule works because it matches experiments, not because it follows inevitably from the theory's structure. Empirical success substitutes for explanatory grounding. This suggests quantum mechanics might be complete within a restricted domain. It describes how systems evolve. It predicts measurement statistics, but it doesn't describe measurement itself. That process lies outside the theory's explanatory reach. This isn't necessarily a defect. Physical theories have boundaries. Classical mechanics doesn't explain atomic stability. Thermodynamics doesn't explain entropy at the microscopic level. Recognizing a theory's limits isn't the same as declaring it incomplete. Limitation does not imply inadequacy, but the measurement problem has a different character. It's not about phenomena outside quantum mechanics' intended domain. It's about the theory's internal structure, the fact that it requires two fundamentally different rules for time evolution without specifying when to apply which rule. This creates a conceptual gap at the center of the formalism, not at its edges. The tension is internal, not peripheral. Some argue this gap will eventually close through deeper physics. Quantum gravity might provide a natural collapse mechanism. A unified theory might absorb measurement into a more comprehensive framework. The problem might dissolve when we understand how space-time and quantum fields connect more fundamentally. These are possibilities, not predictions. They assume the measurement problem is temporary, a sign of incomplete understanding rather than a permanent feature of how physical theories relate to observation. Hope here precedes evidence. Others suggest the gap is structural. Perhaps theories can't explain their own connection to observation without invoking something external. Perhaps measurement represents the interface between mathematical description and experiential reality, and that interface isn't itself describable by mathematics. This would mean the measurement problem isn't solvable within physics because it marks the boundary where physics stops. On this view, the boundary is not accidental. Either way, what remains is the fact of the gap itself. Quantum mechanics provides extraordinarily accurate predictions. It describes a vast range of phenomena with remarkable precision. But it does so using a framework that contains an unresolved element at its core. The theory works. The predictions match experiments. But explaining why it works, why this particular mathematical structure connects to definite outcomes in the specific way it does, remains beyond the formalism's reach. That limitation isn't hidden. It's visible in the structure of every quantum calculation that ends with a measurement result. The measurement problem isn't a mystery waiting for resolution. It's a marker of where quantum mechanics, as currently formulated, stops explaining and starts postulating. Recognizing that boundary might be the most accurate understanding currently available. What remains unresolved is not calculation, but explanation.